Hello and welcome to That's Absurd, Please Elaborate. I am one of a number of hosts that we've had over the year that we've been on the air. I'm Trace.
But one of the top two, I'd have to say.
By statistics, yes.
In terms of regular hosting. And I'm also up there. I'm tied, I think, for top.
I think we're tied.
In the top two for hosting episodes. I am Julian Huguet.
And this is a show where we answer absurd or ridiculous or far out or wild questions from the audience, each other, our guests when we have them. And we, do the SciComm. We do the science research. We call people sometimes. Julian's been really good at calling and emailing actual experts to answer some of these questions. So it's been really, really fun.
Can you imagine? I didn't do that today. I was going through, books and stuff instead. So I'm sorry. I got my knowledge that was pre-written down by other people first this time.
Please, at least, was the book searchable on the internet, or did you literally go get it off a shelf and
No,
flip
I have
through
a wealth of old science textbooks and stuff that come in handy.
I'm not going to comment about all of the ways that people are represented in those old science books, but I'm sure that there are some things that
I have to look through that. I definitely do. I do have I've got my coloring anatomy book, which I can make any sort of representation I want in this because I choose the colors. So that's nice.
Oh, that's nice. Wow. That's great.
Anyway.
Well, if this is the first time listening, thank you for listening. Tell your friends about the show if you like it. We are anywhere that you get your podcasts. If you love the show, give us a review. That really helps us grow the show and get it in more places. We are literally almost at a year of making episodes. We're really excited. And this episode is airing on a very special day. It's Leap Day.
Yes, it is.
And if you don't know this about my co-host, Julian, this is his first anniversary of his marriage.
It is. I married my wife on Leap Day 2020. And then shortly thereafter, some things happened, which was kind of a downer. But now, 4 years later, we're celebrating our first anniversary today.
Yay!
She's in Ecuador.
Great. She's in Ecuador.
She left me for the tropics of the rainforests and the marine iguanas, which, let's be real, if you know my wife, you knew that was coming.
Yeah, definitely. Yeah. That's why you love her so much, because she's just like, I have to be with the iguanas now, and then disappears.
The iguanas are calling, and I must go.
She's the Muir of iguanas.
But I look forward. She'll make it up to me, she says, on our second anniversary in 2028.
That seems fair.
Mm-hmm.
Yeah, that's usually how it goes. All I remember about your wedding is that your dad took his pants off, and then it was on a beach in Southern California.
It was.
You guys looked so happy.
Aww.
Everyone was super pumped to be there. And then that we left your wedding arch by a dumpster after we were done.
We did. It was assembled that morning hastily by the groomsmen. And then afterwards, I was like, what do we do? And Trace, as a very, ingenuitive and helpful guest, was like, make a little Craigslist posting. And we'll leave it by this dumpster. And it was picked up that evening by, I think, a Girl Scout troop?
As I recall, the Craigslist post was, wedding arch used once.
Oh, if it was never used, that's right up there with baby shoes never worn.
Some Hemingway stuff. I felt pretty good about it, the way it was. Well, anyway, enough about us. You came to listen to some absurd questions. So first this week is going to be my co-host, Julian.
Yes.
Julian, what was your question?
So Aaron wrote in with a question related to how we cook and prepare food. And Aaron asked,
we all know that microwaves are the most common way to use non-visible radiation to cook your food. I was just wondering, could we use other waves like radio, gamma, X-rays, or ultraviolet to cook food? What would that even do to the food, to me for eating it? Thanks, guys. Appreciate it.
Aaron also goes on to expand that he heard a conspiracy theorist talk about how microwaves are cooking your brain.
Oh.
Yeah. And was talking about 5G after that. And then I guess this made Aaron want to know more about how we could possibly be cooked by other things. So I love how the question wasn't like, is our brain being cooked by our microwaves? It was just like, what else can we cook?
If you're going to cook something, maybe a brain, but if you're going to cook something, whatever it is.
Yeah. Why not gamma rays or X-rays? You know, that was their main concern, not the conspiracy. So that conspiracy theorist did not do a good job of evangelizing, I suppose. But we get to talk about how things are cooked. And maybe we'll lightly dabble in, like, conspiracy theories on your brain being cooked. Or just common myth conceptions about microwave radiation and whatnot. Because I hear them all the time. But before we get into that, Trace, first of all, do you know, I'm going to put you on the spot, the 3 ways that heat can be transferred?
Convection?
Yeah, that's one of them.
Because that's the name of the oven. Convection oven?
You're right. There's convection ovens.
That means it goes through the air, right? That's the convection one. Conduction.
Correct.
That's where it's solids, right?
Right.
I'm looking off into space, thinking like, how do I make my brain remember these things?
He's got a really far away look. Well, you got 2 of the 3, and then the third one, I guess
would be radiation.
There you go. Convection, conduction, and radiation, and they're just as you summarized. CCR. Convection is you warm up some air, and then you waft that air around the thing that you're trying to warm up, and the air transfers that heat energy to the thing that you're heating, right? And so it's good at cooking things from the outside in, like when you want to bake some bread and have a nice crispy crust, but then like a gooey, soft center still. Then there's conduction, which is when you're directly touching the hot thing, you know, like electric stove when the heating coil gets all hot, and then you put the pan on it, and then the touching elements transfer heat to each other. And then radiation, which is when electromagnetic radiation, which is, you know, waves, electric and magnetic fields that permeate everything in the whole universe, they transfer energy from one thing to another. So how is the Earth warmed? This nice, pleasant, warm Earth that we're on. Knowing these 3 means of conducting heat, how does the Earth get warmed? I mean,
the sun releases lots of energy, and there's no air in space. I mean, there is, but it's for all intents and purposes, there's no air in space.
Not a lot of stuff there.
The radiation comes off the sun, and it heats our atmosphere, and the radiation hits the air in our atmosphere, and then it gets excited, and that generates heat.
Right. So from the sun, because we're not touching the sun, I hope.
Right. Oh, no touching. Touching.
We're quite far, and there's nothing, you know, no air in between us for convection, right? The sun transfers energy to Earth through radiation. So yes, everything here, basically, we're getting heated by radiation ultimately from the sun.
Nice.
So when we're cooking, right, you can use these 3 things, convection, conduction, radiation. And also, as alluded to by Aaron, right, you may use a convection oven, or you might use a microwave oven.
Right.
Right. So microwaves, though, I think are a cause for a lot of conspiracy theorists because, first of all, I don't think the name is doing it any favors.
No, not really.
Yeah. The funny thing about microwaves is the waves are, relatively speaking, they're pretty big, you know?
How do you mean big? Like, well, it says micro, so in my mind, you say microwaves, and I picture tinfoil hats, and I picture, of course, the microwave oven, and I picture this guy I used to work with. He was my boss, and he found a microwave in the trash, rebuilt it, and then used that, and so we would all turn our groins away from the microwave anytime it was running, just to be safe. So that's what I think of when you think of microwave. But tell me, how big are microwaves?
You could have made tinfoil underwear. I don't know. I'd save yourself a step, right? If you're wearing a hat.
Man.
I feel like it'd be easy to fashion.
Well, we were wearing historic outfits during this time.
Yeah.
So it wasn't historically accurate to wear tinfoil.
But the microwave was fine. The microwave was historically... My dearest Gwendolyn, we're out of Hot Pockets.
And then she just writes back, do you have any lean pockets?
I long for the day when another shipment arrives. The turntable in the microwave has broken, and I'm afraid there were several hot and cool spots inside of my microwave. War is hell.
Stop.
It's full stop. Okay. Now carry that on a horse over to Gwendolyn. All right. So, microwaves, when we're talking about electromagnetic waves, right, there is a spectrum. And it goes from smallest waves, which are down at like the gamma rays, X-rays, and to the largest waves when we're talking about radio waves. And when I mean large, I mean the distance between one peak on the wave to the next peak. That's your wavelength, right?
Right.
Visible light is measured in a wavelength of nanometers, like 380 nanometers, that's your deep dark purples, to 700 nanometers, that's red. Radio waves, I mean, they can be meters to several meters, like very, very, very long radio waves. Microwaves are in between that. They are larger than waves from visible light, but smaller than radio waves. So
interesting.
In your microwave oven, the wavelength that's bouncing around in there is about 12 centimeters, or a little under 5 inches. So when we say micro, they're not
really micro. That doesn't sound micro.
They're not that micro. They're micro compared to a radio wave, but not compared to, most other waves, in fact. So, do you know how microwaves work?
I did a video about it once.
You did?
I did.
I feel like you're going to steal a lot of my thunder then, so I'm not going to let you tell everybody.
I will say that the neat thing about microwaves is if you put like a bit of chocolate in the microwave and you disable the turntable, it will melt only the wavelength. So you can measure the exact wavelength of your own microwave. Yes. And if you do the right calculation, you can get the speed of light from that as well.
Oh.
Which is cool.
So fancy.
Yeah.
But yeah, you're exactly right in that, these waves travel through your food, but the way that they heat your food is what I'm looking for. And it's different than the way infrared radiation might heat your food.
Ooh, cool.
Yeah. So the way it works is your food has water molecules all throughout it, right? Water's just everywhere, pretty much, in organic material. And water is polar, right? You think of water molecule, you think of like the little Mickey Mouse kind of looking structure, right? Your big oxygen with your two little hydrogens stuck on at
the Steamboat Willie Mickey Mouse, which is now in public domain. We can think about that all we want.
So we can use that in our Instagram when talking about this.
We actually can.
We're going to do that just to be stir the pot a little bit. Yeah. Use a cooking metaphor. So the oxygen is more electronegative, meaning it attracts the electrons that it's sharing with hydrogen more than the hydrogen does. So the oxygen has a bit of a negative charge, and the hydrogen molecules have a bit of a positive charge. And because it's in that Mickey Mouse shape, you basically get a polar molecule. One end is more negative than the other end. Because of that polarity, water, first of all, has a lot of super useful properties, like breaking down other polar things, but it also aligns with electric fields. So if you've got an electric field, water will basically rotate to line up with it. But then if you switch the direction the electric field is pointing in, water flips the other way.
Yeah, and that's the molecules, you mean?
Yes.
Yeah.
And that's exactly what's happening inside your microwave. Your microwave is generating these electromagnetic oscillations that go back and forth, and the water molecules in the food that you're cooking are bouncing back and forth with it.
They're just like flipping around in there and doing a little like, whoa, 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 whoa.
They're doing a whole bunch of 180s, right? And they're doing, microwave, the frequency of a microwave is typically about 2.45 gigahertz, right? Which is 2.45 billion oscillations per second.
That's a lot of flipping.
Yeah.
That's a flipping lot of flipping.
That's a flip ton of flipping.
That's a flip ton of flipping.
So the water in your food is trying to bounce back and forth 2.45 gigatimes a second.
Oh my God.
It's a lot.
That is a lot.
It's a lot.
No wonder it heats up.
Exactly. So
it's flipping out.
This motion, right, it causes friction with the molecules around it, and it heats up your food, and it heats it evenly throughout, which is why you can't bake bread the way you would in a conventional convection oven, right? But you can heat up food like a hot pocket very quickly.
A pizza roll?
Yeah, leftovers, delicious lasagna. And as you mentioned, though, part of an issue with microwaves is how you might have some areas they get cooked and others that might not.
Right.
And this brings us to my first part of my answer for Aaron's question, which is why microwaves are ideal for cooking in the way that we use them. And that is because of that wavelength, right? You can make a microwave that is the correct size to bounce those microwaves around inside that little resonance cavity of your microwave. Yeah. So if it doesn't go through your food and cause your water molecules to flip back and forth, it doesn't get wasted. It bounces around and comes back.
It might go if it misses the first time, it might hit it the second time, or if it bounces 3 times, the third time.
So you can get a lot more out of the energy you put in than if you just like pointed this magnetron in open space at your food and then just tried to eat it that way, right? Also, the metal walls of the microwave bouncing the radiation back and forth means it doesn't leak out and, cook things it's not supposed to.
Yeah.
Like your brain nearby. If you've got your face pressed up against the glass.
Yeah.
Waiting.
Yeah, I remember when I did the video about it, I was like, the holes in the window of the microwave, the tiny little holes, the reason that they're that size is to block the waves that are trying to get out. You can still see through because visual light, much smaller, can come right through. But like these microwaves hit that, and it's essentially, to them, it may as well be solid.
Exactly.
So they just bounce around inside of this cube of metal, even though you can see in and out because science is great. Science is great. Flipping great.
So cool. And so your microwave is basically a Faraday cage there, so it's preventing that. I know, such a great word.
Faraday cage. Anytime somebody can work Faraday cage into a conversation, you're winning.
It's going to be a Faraday.
Yeah.
Yeah, so the Faraday cage of your microwave, right, keeps like the electric waves from passing out of it. And but because stuff is bouncing around inside your microwave, these waves are bouncing around, you get standing waves where the waves interfere with each other. And at some points they amplify how much, oscillation there is. And at some points they cancel out. And you get these nodes where there's no change in the electric field. So the molecules of water don't flip back and forth at those points. So if you disable your turntable and put a bar of chocolate in there at those points, chocolate doesn't melt. Yeah. Just like in your video.
Yeah.
So microwaves are useful for those reasons, right? They get water to flip back and forth, lining up with that. They are small enough that you can actually bounce them around inside like a little device that'll fit inside your kitchen. Radio waves could theoretically also be used to cook. In fact, I found a company called Nofima. I think they're Norwegian.
Okay.
And they are developing like large-scale radio wave ovens that do exactly the same thing that microwaves do. And the idea is you can cook like bigger stuff that won't fit in your little microwave oven. You can cook
How big are we talking? Like mammoths? Like you want to cook a whole mammoth?
I think it's really up to, how big your radio wave is, how big like I guess at this point, the room you want to set up to cook stuff in. Yeah, but you can make things bigger. There's also the issue that the bigger wavelengths do not carry as much energy.
Sure.
So you've got to also, up the amount of energy you're putting in.
Yeah.
But apparently, one company is experimenting with this method of cooking food.
I'm like picturing just a gigantic microwave, like from a cartoon.
I mean, essentially, that's what it is. It's a macro microwave,
a
microwave oven.
A macrowave.
Ooh, we need to get in touch with this company and propose our.
You got to call it the macrowave.
The macro microwave. The macrowave. Okay.
And then the slogan should be macrowave. It's flippin' great.
So yes,
it's a double meaning because
because
it's great.
Because it flips the water.
It flips it well, and it's also good at it.
Yeah, flipping good at it. Okay. You're so stupid. Okay,
so stupid.
You're so dumb. let's compare that, though, to how infrared heats stuff, right?
Yeah.
Like the heat from the sun's infrared, and there are infrared ovens as well, and they're also useful for like industrial applications. Let's say you don't want to heat a big mass of air and then move that around to cook your food. Well, you can instead, heat up something to the point that it's emitting infrared light, and that light is directed at whatever you want to heat up, and that transfers that heat. There's also infrared heaters. You're probably familiar with them if you've ever been like outside somewhere and there's just like a big coil.
A restaurant or something.
Yeah.
Yeah.
That's not heating the air in the outdoor space, because that would be a huge waste of energy, right? But instead, it's transmitting infrared radiation at you, and that's warming you up, right?
Got it. Don't tell the conspiracy theorists that. They will never allow them to be turned on in any restaurant.
This is really going to blow their minds, Trace, because here's the thing.
Uh-oh.
Everything that is above absolute zero Kelvin, negative 273.15 Celsius, everything emits radiation. And most of it at the temperatures that you and I exist at is going to be infrared.
Infrared.
Right. It sounds like a really cool, like VHS opening title thing.
Yes. Everything about that was very cool.
That was so vaporwavy. So
everything gives off radiation.
Everything.
We are currently giving off radiation in the infrared spectrum.
Right. So to visualize like how things give off radiation, there's a theoretical thing. You can think of it as black body radiation. A black body is like a theoretical perfect emitter and absorber of radiation, right? And there's equations that describe, okay, if a black body is at this temperature, you can expect the radiation it gives off to look like this, right? And it's like a curve of some of it'll be visible light, some of it'll be infrared, blah, 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 right? But a lot of it skews more towards infrared, which is why we have, infrared cameras you can just put on and look at stuff. Yeah. And these cameras see the infrared radiation and then just translate it to something that we can see.
Yeah. We usually use the word heat to describe those cameras. We're like heat vision.
Right.
And what it really is infrared vision.
Right.
You're just using something that's slightly on the redder end than we can see. Some animals can see into infrared. Obviously, the James Webb Space Telescope can see into the infrared. But we humans can see only into red. We can't see into the infrared.
Right. So infrared is longer wavelengths than red, but shorter than microwaves.
Right.
Now, infrared, we all give it off, right? As because we're warm, I should hope. We're above 0 degrees. We're above 0 Kelvin.
Yeah.
But infrared also has an interesting property with how it interacts with molecules. It transfers heat not because it causes water to flip back and forth the way that microwaves do, but infrared radiation excites the covalent bonds that are holding the molecules that make us up together, right?
Ooh.
Yeah. Which might be, I think, something that's often lost on people when we always say, oh, infrared is heat, but like, how is it transferring the heat?
Right.
Okay, well, covalent bonds are when atoms are joined together because they're sharing electrons, right? That basically puts them both in a more stable state.
Covalency.
Right. But these bonds you can kind of think of them as like springs. They can bounce back and forth, like vibrate. They can twist. They can bend towards each other. So infrared radiation is exciting the electrons in these bonds and causing them to stretch and vibrate.
Yeah, I usually think of it like two really strong magnets when you're holding them near each other, and you can feel how powerful they are. Even if they're not touching, you can still feel them, like kind of moving around and stuff. That's what I think of.
Right. There's a force holding them together, even though
exactly.
So electrons absorb electromagnetic radiation, right? The reason that we see things in general is because like light hits something, the electrons in it absorb it, they jump to a higher energy state, but then they fall back down again and they emit a photon, right? More electromagnetic radiation instead. In the infrared range, instead of emitting light again, what's happening is these molecules are having the electrons that, join the covalent bonds. Those are absorbing energy, but it's causing them to vibrate. And if the infrared radiation is at the same frequency that these things naturally vibrate, it causes them to vibrate more. And temperature is just a measure of how much molecules are moving.
Yeah.
That's it.
Yeah.
Right? So if you cause the increased vibration and moving around, you're going to increase temperature. So you can warm things up with infrared. But when we start getting to higher wavelengths, now we're not causing molecules to flip back and forth like we do with microwaves. Now we're not causing them to vibrate like we do with infrared. We start getting to the point where we just straight up start damaging them.
Yeah. I think it's just worth mentioning on the spectrum again, right? So we've got super long, radio waves, then we get slightly less into microwaves, we get slightly less into infrared. They're getting shorter and shorter. Then we get to the visible range, which is already pretty short, and now we're going on the other side of visible into ultraviolet, into, X-rays, gamma rays,
right,
etc.
Right. So that's where I'm going to go.
Teeny tiny.
Is X-rays and gamma rays, which is very, very, very short wavelength, and as a consequence, very high energy. So much so that when the electrons in atoms absorb these wavelengths of light, instead of the electrons jumping to a higher energy state, then coming back down again and emitting it, or just vibrating like they would with infrared, they can get ripped clean off.
Whoa.
So this is called ionizing radiation, because it takes something that wasn't an ion, right?
Yeah.
It's a evenly charged, neutrally charged atom or molecule or what have you. It rips an electron off, and now that molecule, that atom, whatever, has a net charge.
Yeah.
Well, this can be super disruptive to, how your body works. Chemistry depends a lot on things having the correct charge for them to function. So if you start ripping electrons off, you can damage molecules, you can damage DNA, and you can cause radiation burns with X-rays and gamma rays. But that's not the same as warming it up to the point that, it's hot and it burns. That's literally destroying the actual cell to the point that it hurts. It's like a burn.
Yikes.
Same that's what a sunburn is. That's UV radiation ionizing.
It's damaging your skin. We think of it as a burn, but what it's really done is damaged, destroyed parts of your skin.
Yes.
And you're having to deal with the healing of that now. But it's not really the same as that was hot, I burned it. You know?
So X-rays, gamma rays, they carry so much energy that they damage whatever you're trying to cook instead of actually just transferring, heat into it. It would also be difficult to, put them in a little convenient box like your microwave, because you'd need lead shielding to keep those teeny tiny little waves from getting out, right? You couldn't have the little glass window and watch your Totino's rolls steaming up or anything, because it would just fry your eyeballs if you looked through it.
I swear this episode is not brought to you by late night food that we made when we were maybe we still make.
Listen, my wife is traveling. I'm living off of microwavable foods. That's not to say that she cooks. I do the cooking. It's just now I don't have to.
Now you don't have to.
Now I get to indulge the worst parts of my inner 5-year-old.
Yeah.
So
Tino's pizza rolls with ranch. Or ketchup.
Gross. Wait, no, can't be a pizza. This is being a pizza bigot. We covered that. Okay.
Yeah, true.
Can't yuck your yum.
No pizza bigots.
No pizza bigotry. So could you transfer energy and heat these things up? Yeah, but you'd actually end up damaging, your food a lot more than anything. And it would also be a huge waste, and it wouldn't be particularly convenient. So X-rays and gamma rays, not an ideal thing either. So really, when it comes to cooking, we are restricted to maybe radio waves if some companies want to develop this, but really more conveniently, microwaves for practical purposes. And then infrared as a very typical standard way of cooking that I think Aaron may not have realized was used as much as it is.
I mean, a solar oven essentially is using that kind of system, right? It's using that infrared radiation from the sun, and it just like reflects it all back at whatever you're cooking.
Yep.
Pretty common.
Yep. Or just straight up, like I said, some large industrial operations with like big old ovens use infrared ovens. You don't want a big convection oven because you're wasting so much energy.
Yeah, you'd waste it heating up all that air.
Yes. So as for 5G...
Oh, yeah. Back to the conspiracy theories.
And whatnot. Well, again, one of the important things we talked about with your microwave oven is how it is a resonance chamber to bounce those waves back around inside and reuse that energy. When we're talking about cell phones or Wi-Fi, you'd be surprised. Wi-Fi is at a remarkably close wavelength to your microwave ovens.
Yeah.
Microwaves, depending on, right? There's 2.5 gigahertz Wi-Fi. There's 5 gigahertz Wi-Fi, which is not the same as 5G, by the way, because that's like 5th generation, because everything's confusing when we talk about electronics and technology. So yeah, older Wi-Fi that uses 2.4 gigahertz and microwaves that are 2.45 gigahertz, actually there used to be issues with them interfering with each other if the microwaves weren't shielded well enough.
Yeah.
So you don't get cooked by your Wi-Fi, and you would notice because you would feel hot. But it's not using energy, these waves, to actually, move molecules around. That's not the purpose of your Wi-Fi. It's just to carry a signal that your phone can detect. And so it doesn't need to be at the power level that your microwave oven is for heating up food.
Yeah. There's not enough power in those waves.
Right.
If you think of it as like active and passive, it's not really what it is, but the Wi-Fi would be more passive than a microwave, which is maybe more active. Again, that's not a good descriptor, but...
So if you don't feel, say, your junk heating up when you're working at some sort of park where somebody stitched a microwave together that they found in the trash... If you don't actually notice anything getting hotter...
We never did.
That's pretty good evidence that it's not cooking your brain.
Yeah.
Or
and
anything else.
The 5G waves are they call them millimeter waves or whatever, right? But they're basically radio waves. They're in the radio wave near the microwaves, not quite. They're like 3 orders of magnitude bigger than microwaves or something. It's like they're quite large. So even though people are like, 5G is going to cook your brain, it's like it's way bigger than a microwave. Way bigger. And not bouncing around.
Is water starting to boil near the 5G towers? Like, no. Then based on how we know microwaves work, by moving these water molecules back and forth to heat things up, unless you're feeling hotter, you're not getting cooked.
Cool.
Yeah.
Good to know. Well, thanks for your question, Aaron. And thanks for answering it, Julian.
Oh, thank you.
Yeah. And let's take a quick break, and then we'll come back and answer my absurd question, which I think is pretty good.
I'm going to pop something in the microwave.
Julian, give me your best dinosaur roar.
Oh, God, an asteroid! It's horrible!
Wow, that was not where I expected that to go. We're popping in before the show to tell you about I Know Dino. It's a dinosaur podcast.
We think of those dinosaurs being this thing that's been dead for tens of millions of years. Even so, studying dinosaurs can still teach us stuff that is relevant to the world today.
Yeah, like climate models to help us understand global warming.
Migration patterns of dinosaur lineages, they tell us about Earth's changing continents.
We can also study dinosaur diets, what plants lived then and maybe what animals and how they interact.
And, this is super cool, many dinosaur injuries, paleopathologies, they're the first known occurrences of diseases.
And they talk about all this kind of stuff on I Know Dino. It comes out every week with new dinosaur stories that you're not going to hear anywhere else. Like, I hadn't heard of a lot of these, which is pretty cool.
You can find I Know Dino on Apple Podcasts, Spotify, wherever podcasts are. And if you found us, you can probably find them. Go check them out. Welcome back to That's Absurd. Please elaborate. I hope you had a good minute or two to go ahead and, warm something up, settle in, get cozy on this wonderful Leap Day. Do you celebrate Leap Day, Trace?
I don't know what to do to celebrate Leap Day. I think Leap Day should be one of those days where it's like, this is extra, so it's a vacation day. It should be a day off, just no matter when it falls.
Ooh, I like that. I like that. I also think we need to make up Leap Day traditions. Like, I think lasagna, because I mentioned it earlier, needs to be a Leap Day tradition.
Nice.
And you can't wear matching socks.
Oh.
Everybody has to wear mismatched socks. That's my bid. If you have a bid for a leap day tradition, let us know.
Yeah, please.
Tell us on Instagram or something, because I want to come up with some. And we'll do them 4 years from now.
Right. We need some leap day traditions. Tell us now. We'll have plenty of time to get ready for them in 2028.
Well, Trace, what is your question for this episode?
So my question comes from Silas in the UK, and Silas asks, what is soup?
Oh, no.
What is soup?
Are you asking me?
That's what he's asking. And he goes on to say, it should be simple, but almost everyone I know disagrees on the definition of soup. I feel like we're going to have to unpack that a little bit. And then he goes on to say, is the ocean soup? Is water just hydrogen soup? What is soup?
I'm thinking of that Arrested Development episode where Buster's like learning to fend for himself, much as I have been, and he's just got like a piece of ham in boiling water and he serves it. And they're like, what do you call this? And he's like, hot ham water. Somebody tries and they're like, oh, it's so watery, but with a smack of ham.
Oh, wait, maybe that's a very thin soup. I don't know.
Hot ham soup.
Is it soup?
Hot ham water soup.
So yeah, I saw this question from Silas, and I just want to throw this out there. Silas, if you are listening, and I hope you are, thank you. These are my favorite kind of questions because they are so ridiculous. And yet, in this case, there is an answer, and it's a good one.
Oh,
I'm
yeah?
excited about this. Yeah, I drilled down and I really got to the alphabet soup of this, figured it all out. And I'm trying to think of some soup puns, the Bisky Center. Yummy. So, Julian, what is soup?
But that's your question.
Yeah, I know. What do you think?
This is cheating to just offload it on me immediately.
Okay. Is cereal soup?
Oh, crap. Okay.
Right? Exactly. You don't have to answer, but just think about it for a second.
Okay. Let me try and think about what I think soups have in common based on soups that I can come up with, right? We've got things like, we got some minestrone.
Yeah, sure.
We got...
Before you get too far on this track here, is spaghetti and meatballs soup?
I mean, no.
Why?
Well, okay. So first of all...
Okay, so Wikipedia says...
It has to be liquidy. Right. There has to be liquid, right?
Wikipedia's first thing, if you go there and you're like, what is soup? It says soup is a primarily liquid food. It also goes on to say it is usually hot or warm, but it can be cold or cool. It usually has meat and veggies with stock, milk, or water.
Right. I think it has to be savory, right? Because the cereal question kind of blows the...
It might. But there are sweet soups.
Are there sweet? What's a sweet soup?
There are lots of different types of soup. So let me go with the people who know more than we do. People who cook.
The soup experts?
Yeah, which maybe you think of the French when you think of cuisine and soup. Traditional French cuisine has a few different things. Clear soups and thick soups. Clear soups are further subdivided into bouillon and consommé. So they're just different types of soup. And I'll get back to this in a second. Thick soups could be things like purees, which would be a veggie and a starch, a bisque, which is typically a shellfish and a veggie and cream, and a velouté, which is got some kind of main thing, veggies or meats or whatever, and then eggs, butter, and cream. There's also fruit soups, dessert soups, legume soups, like a peanut soup, and so on and so forth. So there are so many different types of soup. But that didn't really answer this question to any kind of satisfaction.
No, I'm hungry for more.
Excellent. So I found a book published in 1900 by Henry Smith, The Master Book of Soups, 1001 Titles and Recipes. Within this, Smith acknowledges there are thin and thick soups, but that soups fall into three categories, BCP. Under B, we get bisques, borscht, bouillon, broths, and bouillabaisse. Borscht, by the way, blood soup, now usually considered beetroot or cranberry. Under C, we get chowders, consommé, clear, and crème or cream soups. And then under P, we have pottage and puree soups. Pottage, by the way, is a thick soup or stew made by boiling vegetables, grains, and if available, meat or fish.
So wait, his entire categorization is solely based on like what letter people tend to use when they describe it? I
mean, so each of these are different things. So like a bisque, like I mentioned, is a shellfish mix with cream to thin it out, so it's primarily a liquid thing again. Borscht is primarily beetroot, cranberry, or blood, depending on when you're talking and what country you're in. Bouillon is, a different type of soup. Broth is a thinner version. Bouillabaisse is different, so it's sort of trying to create a taxonomy of what's in the thing that we're making, even though they're all considered soups.
Okay.
The thing is,
soup family.
Yeah, exactly. If you think of it as like a kingdom, phylum, class, etc., this would be under the family name of soup. And it's not all the way down to the species, I would imagine, because, there are all sorts of different kind of bisques. So maybe you have like a family of soup, and then you have like the phylum of bisque and the order of something, whatever. Like you could get crazy if you want. But 90% of soups fall under BCP. So you can do 90% of them that way. But Silas doesn't really ask about food. They ask about things that are non-food items. Ocean, the water being hydrogen soup. And so just like you were sort of getting at the top here when I asked you to literally answer my question, if you think about it, chicken noodle soup, it's a liquidy wet bowl with a bunch of stuff in it. The ocean is also a wet bowl with a bunch of stuff in it.
It feels a bit misleading, but
sure,
technically not wrong.
Right. So soups, and they can be hot or cold, and the ocean would be on the cold side. So yeah, sure, if you want to call it a soup, sure. But I think part of it is that it's cooked, but not all soups are cooked. So that can make it tough. I mean, the problem is, like with anything, the points are all made up and none of it matters. And yet, chemistry does have words for things like this. So we could go to chemistry. That's where I went next in my research to find out about how to explain what soup is. And chemistry is what cooking is. I just finished the show Lessons in Chemistry. It was pretty good. Except the dog that they chose to play the dog from the book didn't exist at the time that the show was set, which really bothers me, actually. It was a golden doodle, and they were created in like the 1980s or something, and the show is set in the 50s. It doesn't matter. Doesn't matter. So the kitchen is just a science lab where we take raw materials and we turn them into nutritious, edible meals.
Right.
So it's really a chemistry lab. And you can't even say like, oh, well, everything in your kitchen is food. And it's like, well, flour cannot be eaten without processing it and cooking it first, right? A lot of our food isn't really food until we add heat and time, or pressure, if you have a pressure cooker. So chemical changes, physical state changes, whatever. The thing is, chemistry has words that help us answer what soup is. So in chemistry, you have everything, right? Everything in the universe. Then you split it into mass and energy, or matter and energy. So matter is like stuff, atoms. Energy, we were just talking about it for the first half of the podcast. It's things that cause changes in matters, waves, light, sound. So if we stick to the matter side, pretty sure we could all agree. Soup, probably not energy. Probably on the matter side of things. So if we further subdivide matter, chemistry has two different categories: a pure substance or a mixture.
Okay.
So a pure substance would be an element or a compound. That is further subdivided. So elements are one thing. Oxygen, just O2, that would be element. O is an element, right? Iron, just Fe, that's an element. And a compound is two or more things that are chemically combined. So H2O is a compound. NaCl is a compound. It's elements made into things. However, on the other side is mixture. And this is where we get to soup. A mixture is two or more substances mixed, but not chemically combined.
Okay. So water being a pure substance.
Right.
That's out as soup.
Yes. If you were to say pure water, what would that be? That would not be a mixture. That would be a compound.
Right.
However, what if I ask you if seawater, is that a mixture or a pure substance?
Definitely a mixture, because seawater's got dissolved sodium and chlorine in it.
Exactly. It's got all sorts of stuff in it. So then I've got a quiz here. What about concrete? What is concrete?
Concrete's got to be a mixture.
Right. Mixture, for sure. Pure oxygen, pure substance.
Pure, yeah.
Air.
Mixture. Got nitrogen, got CO2. Yeah. Right.
We've got stuff in the air, too, like particles, dust.
Oh, yeah. Lots of stuff.
All sorts of things. Salad.
Mixture.
A cup of coffee.
Mixture.
In fact, most things are mixtures. So if we subdivide mixture into two more things, we've got homogeneous mixtures and heterogeneous mixtures. So under homogeneous mixtures, you also have things like a solution, which is two or more substances in a physical state. So like a perfect mixture. And then a solution, by the way, is a solvent with a solute dissolved into it. So like gases into a liquid, gases into a gas, liquids into a liquid, solids into a solid liquid, liquid into a liquid, very mixed. So a solution would be, to go back, seawater is a mixture, but it's really a solution. It's a liquid solvent of water with solids and gases as the solute dissolved in it.
And if it's getting into your boat, it's also a problem.
We're going to need a bigger boat or a sump pump. But what about bronze? Would you consider bronze a solution?
Well, bronze is an alloy.
It is.
Yeah. It's, I want to say copper and nickel?
Copper and tin. Really close. Really close. Yeah. So it's a solvent of copper with tin melted, mixed, and cooled inside of it. So the thing about a solution is it's mostly one thing with a little bit of other stuff. So soda water is CO2 gas in a liquid. We use a lot of solutions in cooking. Vinegar is an aqueous solution of acetic acid. Baking soda is actually a specific thing. It's a NaCHO3, so that one's a compound. And then we have simple syrups like sugar and water dissolved together. Apple juice is considered a solution because it's basically in a single physical state, which is pretty cool. Then there's heterogeneous mixtures, and this is where we get, again, back into soup.
So we're more soup-like.
Soup.
We're zeroing in on soup.
That's right. So we're slowly getting into soup. So within heterogeneous mixtures, which are mixtures that aren't uniform, there are two different groups as well. A colloid, which is a mixture where molecules do not separate on their own. So again, coffee, if you just leave it there, it stays coffee. So that would be a colloid in the heterogeneous mixture. If you added something like milk into it, sometimes the milk's going to settle out, but probably it's just going to stay mixed in. And then there's a suspension. And that's where the molecules will separate out on their own. So think of oil and water, flour and water, non-homogenized whole milk where the cream floats to the top, natural peanut butter where the oil comes out of the mixture, salad dressings where you have to shake them. Basically anything in your fridge or in your pantry that says shake well before using is a suspension. So it's a within mixture, under matter, we've got the mixtures. Within the mixtures, we have a heterogeneous mixture, and then we have a colloid or a suspension. So now that we've gotten to this point, soup is clearly within the heterogeneous mixtures, probably suspensions. Things in the colloids are like butter. That is a colloid. Foam, a gel, an emulsion, a roux. Things that are not going to come apart on their own. Whereas like chicken soup is definitely a suspension because the chicken and the noodles and the carrots and whatever are going to come out of it. However, if you think about it, within that, the broth is actually a mixture of water and chicken stock and little teeny bits of chicken and salt. So you could argue that is a colloid with a suspension in it, which is where this gets really complicated. So again, quiz time, whether it's a heterogeneous or homogeneous mixture. And then bonus point if you can tell me if it's a suspension or a colloid. And just as a reminder, colloids do not come apart on their own. Suspensions will eventually separate. Okay? Cool. So here's the first one.
Ready.
Regular, natural, squeezed orange juice.
With pulp, I assume?
Yes, just like squeezed out of an orange.
Okay. Heterogeneous suspension.
Perfect. Yes, it will separate over time. Granulated sugar.
Granulated sugar is homogeneous.
That would be, that was a trick question. It's a compound.
Minus 2 points.
Yeah, minus 2 points. How about regular old milk?
That would be it's heterogeneous, and I'm going to say a suspension.
It's probably a suspension. Even homogenized milk you should shake it before you, just in case things have settled out. What about mercury?
This is a pure substance.
That's right. Another trick question.
Yeah.
And the reason I throw that in there.
Wise to you.
How about black tea?
Black tea. Why specifically black tea?
Just tea. Yeah, any
tea.
Kind of, yeah,
okay, any old
tea.
Is fine. This is a heterogeneous colloid.
It's a homogeneous mixture solution because it's ideally you've stirred it up enough. In reality, Julian, you're totally right. But how chemists like to think of it as similar to like a black body, like you were talking about. Okay. If I've made tea, I've stirred it up so that it's evenly distributed perfectly within that, as opposed to reality, which is some of it's hotter than others. We had it in the microwave. Some of the water is slightly different temperature. It's not going to uniformly mix, but it's a homogeneous mixture is what chemists like to think of it, and it's a solution because it's...
I'm too pedantic is my problem.
Yeah, you're being very pedantic, which is good. I prefer that. This one I think is really neat. Smoggy air.
Based on everything that we've talked about, I'm going to say... It's oh no, now why is it getting harder? It should be getting easier the more I learn.
Wait till I get to the next one.
I'm going to say it's a heterogeneous colloid.
It's a heterogeneous suspension.
Damn it!
Because the soot will eventually come out of that.
That's what I
mixture.
meant. Shoot.
Yeah.
Shoot.
Okay.
That's what I was thinking.
What about dirt? Just regular old soil. Just say what you said. Just say what I just said.
It's a heterogeneous suspension.
Right. It's a heterogeneous suspension. Okay. Now we're going to do the bonus round. These are the hardest. A chicken egg.
My brain is like seriously cramping so hard right now. I can't even tell you. Heterogeneous.
Yes.
Are we including the yolk?
I don't
know. Suspension.
It's a colloid.
Damn it.
So, according to this professor who I found, and they listed this as colloid. But I think that the chicken yolk is probably not, I don't know, because it's not going to not be a yolk anymore, right? It's still going to be a yolk. Okay. I think I'm done torturing you.
This is harder than I thought it was.
That's very hard. However, it's easier, I think, when you have all of the options in front of you. It's probably tougher on a podcast.
I kept forgetting what a colloid was.
A colloid won't separate, and a suspension will separate.
Okay.
Yeah, that's how I don't have a good mnemonic for it yet. Yeah, suspension starts with S, separate. I don't know. That's maybe a mnemonic we could use. But something like a computer chip could fall under this as well. A computer chip is a heterogeneous mixture of a variety of different things, even though it's a solid, and it's a colloid because those molecules aren't going to separate on their own. Dirty seawater was on something I saw, which is actually a homogeneous solution of H2O with gases dissolved into it, and then solids as well, like NaCl, with suspended solids that can sometimes come out. So some of it's a colloid, some of it's a suspension. It depends on how you think about it. So let's bring this all back to Silas's question and wrap this up. Where would soup fall within that group? If you think about all of these different categories, it's clearly matter, right? It's clearly underneath that group. It's a mixture of matter. And
I would hope it's matter.
Yeah. You could have energy soup, I guess.
Just energy soup.
Yeah. Maybe if you're a fourth dimensional being or something. And then you further divide that into homogeneous and heterogeneous. It's probably heterogeneous, but it doesn't have to be. Some soups are homogeneous. You have like a jus, which you could consider a soup, or a consommé, which is probably more heterogeneous, and things are going to settle out of it. So it could be either way. Yeah. Gazpacho is closer to almost a solid because it's not even cooked. It's just cold blended. So if you think about it, soup would probably fall into at least mixture. We can all agree. However, soup is not chemically combined, which I think is sort of something that trips people up. Even Googling this question and seeing other people talk about it, some people talked about it as like, well, I've cooked it. Isn't that a chemical change? And chemists don't consider it a chemical change. If you cook soup, what you're really doing is evaporating the water out of things. You might be causing some chemical changes within the things inside, but you don't all of a sudden make something that's not a carrot. It's just got less water in the carrot. It's a little looser. Maybe you've changed the state of the fat from a solid to a liquid, but that's still just a physical change. You didn't make carrot noodles. They're still carrots and noodles. But if you burn it, like you caramelize it, then you've chemically altered it, and that chemical change isn't going to come back. And that might be your goal, caramelize some onions. Anyway, so a soup is a heterogeneous mixture, probably a suspension of food, which is essential to the definition of soup. It has to be edible. So water, as we've discussed, is not hydrogen soup because... Do you know why, Julian?
Well, it's just a pure substance.
That's right. It's just a compound. So water cannot be hydrogen soup any more than salt is a sodium chlorine soup. It's not. That's just a compound. So water molecules, because they're chemically combined, cannot be soup. However, if you put something in water, that might be a soup because now you've made a heterogeneous suspension or in a mixture. Science uses things like primordial soup for early life, particle soup for early universe, and so on. But the term soup is used to describe essentially heterogeneous mixtures, right? Like we're creating essentially, without even thinking about it, we sort of know that soups are things like this. So maybe scientists should just adopt the word soup for some things in chemistry, right? Like right now we have to say, oh, this thing is a heterogeneous mixture of particles, compounds, and other substances. So why don't we just call up the American Chemistry Association or something and say, we should just call this soup from now on. That should just be the term. So like seawater is soup, smoggy air is just soup.
You know, I couldn't help but notice, though, from your original definition, that cereal is a heterogeneous suspension.
It is.
So, are we calling cereal a soup? Is that the only criteria for soup?
So here's what I came up with. All het mix suspensions, heteromixture, all het mix suspensions of particles, compounds, and other substances are soup. All of them.
Okay.
Why not? Why not? Why not?
Wait. Trace, behind you is a litter box.
Yes.
It's got litter.
Yes.
It's got cat urine.
Sure.
It's got cat poop.
Right.
That sounds like a heterogeneous suspension to me.
Yeah.
Is that cat poop soup?
Sure. Why not?
Okay.
I mean, it's not primarily liquid, so we might be able to add a definition that it has to be mostly liquid. But hey, why not? If technically a computer chip or bronze is a heterogeneous mixture in a colloid, then that would maybe not be a soup. Only the suspension side would be soup. But, you know, that's not going to settle out on its own, so that would make it a colloid. So I guess I'm going to say not soup.
I think we're being too generous with our soup parameters here.
Here's what I think.
I think by this definition, most of the universe is soup.
Why not? What's wrong with that? Paint is soup. You know, cocktails are soup, although beer and wine is a colloid, so not soup. It has to settle out on its own. Otherwise, it's not soup. It has to be a heteromix suspension. So
is a galaxy soup?
Is it going to settle out on its own?
I mean,
given enough time,
stars and planets. I guess,
because gravity is going to change how it works. I don't know. It depends on anything about it.
Galactic soup.
Yeah, maybe this is one of those like relativity to describe big things or whatever. This is only describing things in certain sizes.
I think soup has to be made by people with the intent for consumption.
Got it. So not, in your mind, not all heteromix suspensions of particle compounds or other substances.
I think particle soup is just a metaphor, and we can't read too much into it.
Okay. Is blood soup?
Okay, crap. That is made by humans. Well, I mean,
it's not made
for consumption.
Yeah, it's different. I hear what you're saying.
Prepared by humans for consumption. I mean, a borscht, though, like you said, is a blood soup.
Yeah. So would blood sausage be soup?
But it's gotta be liquid.
Aha. See,
right.
So I would say blood sausage isn't soup because it would be a colloid. It's not going to separate on its own. Blood is a homogeneous solution of salts, urea, and glucose, but also a heteromix colloid because the proteins are dissolved in it and won't come out naturally. But if then you were to take blood out of the body, you would also see it's a suspension heteromix of red blood cells in a plasma. So blood is a soup depending on how deep you want to go.
It's definitely soup for vampires.
Either way, there's no real answer to this question, right? What is soup is very specifically a food product that humans prepare, right? And cuisine-wise, we have all of these definitions of what soup is. Silas asked kind of almost a physics-adjacent question, like, is the ocean soup? Sure, Silas, why not? It's a heteromixture solution of a variety of different things suspended within water.
I'm imagining a loophole because of my definition where it has to be human prepared of a person taking like a single cooked fish and throwing it into the sea and then being like, there you go, now it's a soup.
All of the ocean is now soup.
Ring the dinner bell.
It's a very salty soup that you should not consume. I love these kind of questions because not only because there's no answer, but it shows us that everything is made up, right? There are so many of these debates. Is a hot dog a sandwich? Sure, why not? Who cares? Sure, yes. Depending on how you define sandwich, absolutely. And people are like, well, is it a taco? And I'm like, yes. And they're like, well, is a calzone? And I'm like, yes. Yes. Why are we so precious about it? Why are we saying like sandwich has to be this one thing that is, and it can't be anything else?
You know, this actually what it really reminds me of, and I think it's appropriate considering my wife is currently off studying evolutionary biology, but it reminds me of a lot of the bones that, you know, people who don't necessarily understand biology pick with like the definition of a species and speciation. Because what's important to remember about like what we call is a species or whatever is we are the ones who made that up, right? The same way we made up what is and is not a soup. And there are things that blur the line. What is and is not a sandwich, right? And at a certain point, it's just like, you can't get so hung up on the terms that we ourselves created. Yes! We do our very best to define it and make it clear, but there's gray areas that you're just going to have to learn to recognize and accept and work around. It's true in biology. It's true all over the place.
It's true in everything. Here's the thing that I wrote, and I love you. That is exactly where I ended up in this as well.
Yay, friends!
I said, is a hot dog a sandwich? Sure. Are motorsports actual sports? No. Is cereal a soup? Sure. Why not? All of these are made up. Their words are all malleable. Taxonomy is complex, and things fall into one or more category or no category at all, and then we have to come up with a new thing or figure out a new definition like we are doing with planet. But so many people are so pedantic, and they get so caught up in like, oh, but you said it was this. And it's like, look, a hot dog is a sandwich because if you zoom out and replace all things with that, you can see that it's all silly and made up. Like, it doesn't matter. Don't be so precious about it. You remember in episode 19 when we were talking about whether a tomato is a fruit, and we were like, yeah, it's totally a fruit, but it's actually a berry. And like, is a chicken a bird or a reptile? It's a dinosaur, so it's probably, the answer is yes, I guess. And like, is an insect a crustacean? Yeah, probably. Like, sure. It depends how far you zoom out. Like,
anyway. But there's going to be ambiguity. Don't get so hung up on the thing.
Yes.
Right? And then go like, or reject it entirely because things don't all neatly fit, right? That I think is an important one. I know that there are people who, because of these like, oh, what is and is not a species? Well, you know, these two things, we say they're different species, but they can have viable offspring, blah, blah, blah. So that, therefore, all of it needs to be thrown out. No, we're doing our best to categorize things that do not fit neatly into boxes necessarily.
Exactly. Sort of like what you said last episode when we were talking about the design, quote unquote, gigantic, like skyscraper-sized air quotes, the design of the human body. It wasn't. So when we try and break it down and think of it that way, we've already failed. And this is all made up, and we're trying to apply logic and like binary reasoning onto nature, which does not have that most of the time. And so instead, and this is a language which you could argue is just something that we've come up with to try and describe the world. No word is the correct word. They are just the words that we use to describe the things that we're seeing, because they're to try and get a shared understanding. So what is soup? In my definition, soup is a heterogeneous mixture of suspension. It's not a compound. It's not all these other things. However, I could be wrong, and that's fine. It's cool. I think it's a pretty good way. You get like Henry Smith in his book from 1900. You get 90% of it. That's fine. We're 90% of the way there. That's most things. Sure.
So Silas, soup is anything you want it to be.
That's right, dude.
Just believe in yourself.
I think the real problem that I have with this question that I just want to talk to you for a minute, Silas, just you and me personally. Here we go.
Okay.
There's no one else listening. Yeah, just take a second, everyone. In your question you wrote, it should be simple, but almost everyone I know disagrees on the definition of soup. Silas, who are your friends, man? How are you disagreeing on the definition of soup?
Wait. Tell them about this show, though. So they can listen. Be like, look, I know we've had some heated moments about soup.
We can all hate these two guys.
Here's an episode about heated moments and soup.
That's so good. Silas, thank you for asking your question. I really loved it. I really hope that y'all learned something about, chemistry and maybe a little bit cuisine, too. I'm hungry.
Well, I just had my pizza rolls, so I'm good.
Oh, man. Well, you probably heated them up in the microwave.
I did.
With some standing waves. Man, I love our show.
Is the inside of a Totino's pizza roll soup?
Absolutely.
I guess so.
It's a heterogeneous mixture. It might be more of a colloid because it's not going to separate on its own. Like, it's not going to settle out.
No, but I got the pepperoni ones, right? So
yeah, but they're not going to settle out. They're like suspended within.
Yeah. Maybe if I shake them really hard.
I don't know. All right. Well, let's go eat.
Yeah.
Thanks for listening to this episode of That's Absurd. Please elaborate, everyone. The show was created, written, and produced by me, Trace Dominguez.
And me, Julian Huguet.
And it was also produced and edited by the wonderful, wonderfully talented, and hopefully today well-fed Kyle Sisk.
Special thanks to listeners who submitted questions featured in this episode, Aaron and Silas. If you'd like to submit a question, you can look for a form in the show notes or email us at hello@that'sabsurdshow.com or even visit that website, that'sabsurdshow.com/ask. We love getting these questions. We see them pop up in our little feed in our internal Slack channel all the time. They often bring a big smile to our faces, even if we don't actually use them in our episodes. And we're always, thinking someday in the future we just might use them. So keep them coming.
Thank you so much for those who have sent questions. And a special, special thanks to any of you who are listening who support the show in whatever way you do, whether that's sharing the show with your friends, telling your friends and family about it, listening to it in mixed company, talking about what we talk about here on the show with your friends or your family or strangers on the bus or whatever. I really appreciate everyone who's out there listening to our show and thinking about it after they're done listening, and hopefully talking about it too, because that's like half the fun.
And remember, if your brain is boiling next to a 5G tower, put on a tinfoil hat.